Okay. So good morning to everyone. This is session 4 of this fair workshop. And today we will talk about the quality in machine learning. In particular, we will see some contribution from work package 5.5, 5.6, 5.7, with a little incursion from work package 5.3, and in collaboration with TP4. My name is Annalia Corella, and I am a researcher here at the department DIAG. So just to have a look of the contribution of today, we will have some contribution from researcher from Sapienza and from Leonardo. And these contributions are in collaboration with some other university and with the CNR. In particular, we will see that the paper and the work presented are in collaboration with the University of L'Aquila, but also University of Liverpool, Bocconi, and as we already mentioned yesterday, with the University of Pisa and the CNR. The major subject of today is machine learning, of course, and in particular neural network and deep network. We will see also some contribution upon the graph transformer models and imaging processing. Looking into the detail of the program of today, we will have we will start with Lorenzo Colantonio, that will present an efficient graph coloring with neural network. And then we will see the contribution of Matteo Negri with spurious creativity in associative memories, and the contribution of Alberto Facchechi that will present a random matrix approach to the Hopfield-like neural network. We will move then into explainability technique for high energy practical condition from Donatella Genovese, and contrast enhanced pre-processing for CNN-based source camera identification from Silvia Marconi. Then we will close this first part of the session with the progetto Yara from that is a collaboration with Leonardo. And then we will see an added contribution from work package 5.4 that I already mentioned. We will have a coffee break then, and we will move on the last part of this workshop with Luca and Angelo Angelotti. Okay, perfect. So I think we can start. So the first speaker is Lorenzo Colantonio with the efficient graph coloring with neural network, a physics-inspired approach for large-scale graph. Okay.
Hello, everyone. Okay. Hello, everyone. My name is Lorenzo Colantonio, and today I would like to show you my work regarding leveraging physics-informed graph neural network for enhanced combinatorial optimization. So let me start by introducing the problem we studied. We studied the graph coloring problem, a conceptually very easy problem. Let's consider a graph having n nodes and m edges, and given a number of colors q, we would like to assign one of these q variable to each node such that adjacent vertices have different colors. So finding such a configuration is NP-hard, although solving this problem is crucial for many real-world applications such as frequency assignment in wireless network, resource allocation in operating system, and many work shift scheduling tasks. So the problem has been extensively studied using statistical mechanics methods, and there exist multiple algorithms to tackle the problem, both heuristic algorithms, and in the last year, many machine learning approaches have been proposed. Although the question we would like to answer is how can we leverage physical information to develop a novel machine learning model that can outperform the previous proposed one? So let me start by introducing the post-Hamiltonian. As you can see in the image, the Hamiltonian is the one showed in the slide. You can observe that if we take the coupling term JIG equals to -1 for all the couples, the energy of such model is equivalent to the number of conflicting edges of a given graph for a configuration. So we would like to find a configuration, a solution of the model such that the energy is equal to 0. Of course, we can define the Gibbs-Boltzmann distribution and the partition function, and we can use those two in order to compute in the thermodynamic limit the behavior of the problem solution. We focused on the Erdős graphs ensemble. We choose this as ensemble because, as we will see, it's very easy to generate a solution configuration graph for which the solution is known, and this is crucial if you will like to use a supervised approach. These graphs are graph composed by n nodes and are characterized by an average connectivity C. And as you can see, the phase transition as a function of C are well documented in the literature. So for C small enough, the solution from a single cluster, thus finding one of these solutions is very easy. If we increase the average connectivity, the single cluster splits in an exponential number of subclusters, and in this region, algorithms show a slowdown. If we keep increasing the average connectivity, we find a region where the number of clusters becomes sub-exponential, and the state-of-the-art algorithm fails nowadays. So, of course, if we keep increasing the average connectivity, a typical graph will not have any solution that satisfies the constraints. So, we are interested in finding a map from some node feature space to the configuration space such that if we apply this map to a given graph, the energy of the graph becomes equals to 0, and we can approximate this map using a graph neural network, and we can call it f theta. Of course, we would like to train it using gradient descent method, and for this reason, we need to modify the output vector space from the configuration vector space that is categorical to a probability vector space. What I mean is we can assign to each node a probability vector such that the ith entry of the vector can be interpreted as the probability of assigning the ith color to the node. So the architecture we use in order to tackle this problem is the message passing neural network. Is a very general framework, and this is the reason we choose it. The model consists of k layers, where in each layer we perform a message passing operation. The message passing operation is done using two multi-layer perceptron. Then the initial input and all the k hidden node features are concatenated and passed to a third and last MLP. We apply a softmax, and this provides us the probability for each node of assigning one of these Q colors. So the loss function used for the training is a semi-supervised loss function composed by 3 different terms. We have the first term that is the energy term. Of course, it counts the number of conflicting edges, and we would like to minimize it. Then we have the second term that is an entropy term. This term is crucial during the first stages of the learning procedures. It allows us to escape from the parameter space that gives us an output, a paradigmatic solution. A paradigmatic solution is a configuration for which every entry of the probability vector is equal to 1 over q, where q is the number of color. And lastly, we have an overlap term. This term is the only supervised term we use in the loss function, as you can see. And We decided to use this term because the training procedure become more robust and the training itself become more efficient overall. So for training, as I said previously, it is necessary to have the solution of the graph. This can be computationally expensive to obtain. For this reason, we decided to use the string graph because we are able to generate graph with knowing solution using the white planting algorithm. So the training set consists of graph having 1,000 nodes and in a wide range. We decided to set Q equals to 5. And the initial node features are noisy solution of the graphs obtained using a Gaussian diffusion process concatenated with the degree of each node. Of course, we trained the model using gradient descent update rule such as Adam. Once we have trained the model, we would like to use it, and we observed that applying the model multiple times ensured better results. Although there exist fixed set points and attraction basins that cause the algorithm to fail, but if we apply a Gaussian diffusion step after each step of the model, this allows us to escape from attraction basins that are not valid solution. So let me show some of the results we obtained. We decided to evaluate the performances of the algorithm, comparing it with the simulated annealing. Simulated annealing is one of the most robust and efficient algorithm used for this kind of task nowadays. So we test our model on a data set of graph having n ranging from 1,000 to 100,000 and an average connectivity in a wider range in respect to the one used during the training process. And as you can see, as you can see, our algorithm outperforms simulated annealing both on an easy task and to the respect to the hard task. And moreover, we can study more in depth and the performance of the algorithm. In fact, we can assume a power law behavior and analyze the parameter as a function of connectivity. And as you can see, our model outperforms for all the connectivities used during the training, the simulated annealing. And both in terms of energy minima found that respect to the number of iterations required to find those minima. Lastly, we decided to evaluate the generalization power of our model, and we decided to apply the model to graph having a different size with respect to the one used during the training. And as you can see, we choose a graph equal a number of nodes ranging from 1,000 to 100,000. And for all the nodes, the fraction of conflicting edges is statistically equivalent among all the graph sizes for all the possible connectivities used. So the key takeaways of my talk are: we proposed an innovative model that leverages physics-inspired graph neural networks to tackle the graph coloring problem, generating the solution using white planting algorithm and using them during the training phase has improved the algorithm's effectiveness, enabling a more stable learning phase. We show that comparing our method with simulated annealing, our method has a significant reduction in both edge conflict and execution time across a wide range of connectivity values. And lastly, the model maintains high performances even for large-scale graph, taking advantage of parallel processing GPUs. These are this is the team. As you can see, we are all from the physics department here at Sapienza University of Rome. And so let me thank FAIR to support the project.
Okay, any question?
What will be your next development in this direction?
Okay, yes. So as you can see in these plots in the left in the left one, you can see the C parameters. It's like the energy that you achieve after using your algorithm, and you can see that it increasing the average connectivity. Although there exist many algorithms that show that after you surpass a certain threshold, if you are able to generate a configuration that has a solution, it becomes very easy to find such a solution, increasing the connectivity. We are exploring that region of the graph, and we have some preliminary results, and is comforting, let's say.
Okay, thank you, Lorenzo. So next speaker is Matteo Negri. Presentation.
Hello, everyone. Thank you for this opportunity. And I'll tell you about the general direction that I'm trying to pursue in the last years. So some of these things I already said last year, but now I have a theory that matches the experience, but also I have a new perspective for people who are interested in how physics can predict something quantitatively about AI, which means very little. But so my idea is, how do we go from associative memories, which are memories, to something that resembles AI, which is creative, but maybe this could be a point of discussion. And this is a theoretical framework. So I am not doing anything real. I'm just trying to simplify as much as I can to still have an interesting behavior. So why physics in neural networks? As I said, we don't have a comprehensive theory of what's happening. So the idea of physics is, let's have a simple but exactly solvable model. And our favorite model are Optil networks, which recently had a Nobel Prize, so I'm very happy about this. And another motivation for Optil networks is that in various contexts, they pop up. And computer scientists don't know why are they interesting. So in transformers, layers of cross-attention and self-attention resembles various associative memories. And also in generative diffusion, recently there's been a lot of discussion about this. And the idea is, in transformers, maybe the forward update of a layer can be thought of as an energy minimization process. And in generative diffusion is the idea of, well, you don't want your generative diffusion to be a memory. You want to generate new things. So in discussing the limits of memorization in this model can give you a hint on what's happening with generalization. So let me introduce quickly the classic Optil network, which is the idea of you have easing spins, so plus and minus variables, these SIs, and you have an update rule. So you know how to update the variables with some couplings J's, IJ's, which are, can you see my mouse? Yes, these couplings, J's, IJ's, and then you take the sum, and then you take a sign, and this is a very simple recurrent network. And the idea is that the memories are fixed points of these dynamics. And what's happening is you want to know how to plant some memories in your couplings. So you want to learn these couplings such that you can have memories, in this case, the rightmost column. And then if you initialize your variables close enough to one of those memories, you go there. And why is physics important? Okay, sorry, this is the learning rule, which is analytic. So we don't have to run an algorithm. We know how to learn this model. And the idea is that the dynamics that I showed you minimizes the energy. And this is the energy that minimizes. And now we can do thermodynamics. So we can run all the machinery from statistical physics, and we can compute storage and memorization as a phase transition, just as in the way you predict water becoming ice. So you have order parameters. In the case of water is density. Here we have the scalar product of your variables against one of your memories, and you call this magnetization. And you have P memories, so you have one of the parameters for each of your memories. And then you have the control parameters, which is the ratio between the number of memories that you're trying to memorize and the number of variables in your system. And so you compute a phase transition. And so you can, again, this was solved by Auffield, and this is why it was awarded for a Nobel Prize. And this is the phase diagram. So you compute how the model behaves as a function of your control parameters, which is alpha, and then you, physics is like temperature. So you introduce kind of a noise in your retrieval. So instead of updating your variables exactly with the rule that I showed you before, you have some thermal noise that flips something that should not be flipped. And the important part is that below this line called Tm, everything that is below that line works as an associative memory, which means if you go to the horizontal axis, you have a limit at 0 temperature, which tells you what is the maximum number of memories that you can put into the model. But notably, this was solved in 87, but with uncorrelated memories. So again, this looks very promising, but it's actually very simple. You're just memorizing random noise, which is uninteresting. So my idea is, let's move this theory to correlated data and see what happens. And I will show you that this completely changes the perspective of an associative memory, because you can go from storage to actually learning to actual generalization. So let me introduce the most important piece, which is the new kind of data. Again, first, these size, before they were just random noise, and now we choose this specific structure, which means that we have binary features. Again, since we have binary variables, we want something that we can retrieve. So we define these f's as plus and minus, as vectors of plus and minus. We have a dictionary size d, so we have d of these features from which we can sample. And then we have binary sparse coefficients, which means that, sorry, and the number of non-zero coefficients is L, which means it's a complicated way of saying that we have each example is a combination of L features. This is the only important thing, I think. Okay. So the idea is we learn from images, and these images are made of elementary features. And then we have new order parameters, which corresponds, instead of the magnetization with respect to examples, we have the magnetization with respect to features. And now we have new control parameters, which is again the ratio of the number of memories, but now we also have the ratio of the size of the dictionary, which is how many features we have. And then also we have this sparsity. How do I move this? Okay. Can I continue? Maybe. Okay. So let's run an experiment. We want to check if a generic configuration x0 is a fixed point. So we do this experiment. We initialize the model on x0. We run the dynamics until we reach a fixed point, and then we compute the distance between the initialization and the fixed point. And we call that magnetization, because we know that this quantity corresponds to the analytic quantity that I want to compute with physics. So in this plot, I show on the vertical axis the actual magnetization that we measure, and on the horizontal axis, the ratio P over N. And then I am using a specific value of the ratio alpha D, which is D over N, and the sparsity L3. So these examples are sums of 3 features. And so as we know, there's a storage phase where if you store a low enough number of examples, you have finite magnetization. And as we already knew, as you increase the alpha, you lose everything. You have something called catastrophic forgetting, where you don't store anything anymore. The interesting thing is that we correlated examples. You have this. So if you keep increasing the amount of examples, first, the network tells you, no, there are too many, I can't remember all of those. But at some point, if you increase by 2 orders of magnitude, the network says, ah, yes, now I remember everything, which sounds weird. So our theory tries to explain what's happening here. And what is happening is that it's not just the examples that the network saw, is that all possible examples generated from the distribution of the training examples now become fixed points of your memory, which sounds interesting. And the theory, I will not tell you about why this happens. It's just that I'll tell you that before this, the network learns the features themselves as memories. And so we want to explain this phenomenon. So as I showed you, we have the feature validations, we have multiple control parameters, and so we want to do thermodynamics, which means we average the behavior of the model over all possible realization of the data sets. So instead of using MNIST or something that has one data set, we come up with a synthetic data set that we can control, and then we compute the average case of all the possible data sets. And this is the partition function of this thing, and must be solved with replica theory. So which is kind of a complicated thing. So I will not tell you anything about this, just to say that it took a year to do this calculation, to put a line. Why this thing doesn't work? Okay, to put a line on this plot. So this line is the theory that predicts the red and the orange lines. And this theory tells us a message, which is the model switches behavior when we have correlation hidden in the data set, because it learns the feature, not the data points itself. And then it learns to combine the features to predict all possible combinations of features. Again, it's a very simple setting, but it's interesting that we can predict quantitatively what's happening. So what's happening is that the orange line corresponds to examples that the network already saw, in this case, these Simpsons characters. Then the blue line corresponds to the network learning the features. So it's like these are the new memories. And then at very high load, the network learns to mix these features in new ways that you never had in your training dataset. And this is why I call this from memory to creativity. And my future perspective is to use this to understand what's happening theoretically in deep learning. So if I have a few more minutes, I'll just tell you something that's unpublished yet, but it's a perspective of how these things could be used in something a bit more complicated than just an off-field network, which is energy-based models. Okay, so let's imagine that we are in a very basic context of maximum likelihood. We have some data, and we want to model this data with a probability distribution. So we have a set of variables, S again. I don't know what's happening. Okay, now the mouse is working. Okay, and so we have a probability on which we can use a likelihood, and then we have a data set, and then a very classical approach is to minimize a loss function, which is the negative log likelihood of the data. So you take your probability distribution, you evaluate it on some data, then you sum over all your data, and then you maximize this with respect to the parameters J from which the distribution depends. But this is very difficult because you have to estimate the normalization of this probability. So usually it's very expensive. And one very used approximation is called the pseudo likelihood, where instead of having the full distribution, you approximate this distribution with a product of conditionals. And this usually is a very strong approximation, but in exchange, you get a new loss function, which is called the negative log pseudo likelihood, which is very tractable because it doesn't involve an integral of our possible variables, it's just marginals. So this is a very famous approach, ubiquitous. And one of the most classical things to do is model your probability distribution with an energy. And this is why physics and the off-field model comes back in. So the idea is that once you infer your energy, basically, you can run sampling, because the idea of having a maximum likelihood or pseudo likelihood process is to infer and then sample from it. And you sample with Gibbs sampling, which means just sampling each variables one at a time with the conditionals that you just inferred with the pseudo likelihood approach. And my message is, this is again an associative memory, but it's secretly. Nobody knows that. Usually this is like a sampling machine. You never go to zero temperature and probe the memory capacity of these objects. And this works. And we tested it on the same data that I showed you before, and it still works very well. But the novelty is that since now you have an algorithm that learns, this also works on real data. So this is the same plot that I showed you before. On the vertical axis, you have the magnetization. Here we call it final overlap, but it's still magnetization. And on the x-axis, you have the alpha, the amount of data. And the blue curve represents the training data. And you see that the model manages to store in memory all the data points until very high load, which is unusual for correlated data. But also test data, again, data that the network never showed before, become fixed point of the network. And the random data is just a check, because if random is stable, then everything is stable and there's nothing interesting happening. So as long as the red curve, the green curve is not 1, interesting things are happening. So around 10 to the 1, we have a functioning associative memory that works both for the training examples and test examples, which I think it's very interesting, because maybe in transformers, there are hidden associative memories. And this mechanism can explain how these hidden associative memories can also help generalization in deep learning. I think I'm done. Okay, and this is an example to see visually what's happening. It's not too bad. So this is the original example. Then we put some noise on it, and then we reconstruct. So the reconstruction is not perfect, but it also works on examples that the network never saw. So we realized that the network is basically learning how to smooth random pixel in some way that it resembles the original pattern. So this is not an application. It's not useful to go to near-ips, but maybe it's useful to build a theory. So the take-home messages are that often networks can store hidden features hidden in the data, can store previously unseen examples, which sounds an oxymoron, but it's what happens, and that associative memories may be hidden everywhere in AI, but this is more of a wishful thinking than not. And again, just to flash you, these are the places where associative memories may be hidden. And I would like to thank you for the grant, especially. These are my collaborators in the 2 projects on off-field and pseudo likelihood. And these are the 2 papers with the theory, if you're interested. Thank you. Thank you.
Potrei aver chiuso tutto? Sì, sì. Ah, ecco. Ma siamo sicuri online? Ok. È sparita la condivisione, ma ci siamo. Ok. Our next speaker is Alberto Faghetti.
No touch screen. Okay. Good morning, everyone. Thanks for being here. As you can see, this mini talk is very close in spirit to what Matteo nicely explained in the previous talk, but the methods are somewhat orthogonal. And you can see, first of all, the theoretical interest is to frame, to get a picture of fundamental mechanisms behind generalization and eventually overfitting phenomena. And this is done in the setting of Hopfield-like neural networks. Matteo explained Hopfield networks, and in this case, we have Hopfield-like neural networks. The first point is that we analyze these models by a random matrix approach. So random matrix theory is a beautiful branch of mathematics, and there is a lot of interesting stuff in that. But it can also be used to analyze generalization capabilities of these models when dealing with data instead of memories. Okay. So the basic point is that artificial intelligence models are large-scale interacting systems, and thermodynamics teach us that in this setting, new physical laws emerge in terms of a low number of state variables, and the physics of these models is described by the concept of phases and phase transitions. And this is we have a peculiar example of phase to the presence of phases and phase transition in artificial intelligence, which is a very familiar situation. In the left, you have a model which is able to generalize from experience, because both the training and the validation errors are close to zero when the training procedure goes to infinity. And on the other side, you have a model which is in an overfitting regime, meaning that the validation error is far higher than the training one. And so the system is not able to generalize from the experience. From a practical point of view, this is an unwanted situation, but from a theoretical point of view, this is a manifestation of, or dynamical manifestation of a phase transition between two different regimes. The one is the generalization phase, and the other is the overfitting regime. Of course, there are a lot of techniques which are used to avoid the overfitting regime. And from a theoretical point of view, this technique, the working principle of these techniques can be used to access the understanding on the working regimes of the lying behind the emergence of generalization. So this is the crucial point of our investigation. Okay, let me introduce the task. Suppose we have two kinds of information vectors. On one side, you have the hidden features, the hidden memories, which can be thought as binary vectors, and they are not accessible, meaning that you have no direct access to them, but you only have empirical manifestation, which are the training examples. Of course, this is an idealization, because in a theoretical approach, we don't have a clear structure of the features and the examples, but they are random variables. The task we want to achieve is a reconstruction of hidden patterns, meaning that we want to design a model in which, if we fed the system with an example, which can be a training or a validation example, you are able to reconstruct the hidden pattern associated with the validation example. So you have, for example, the handwritten digit 2, and as an output of the network, you have the concept of 2. And this is feasible, of course, as Matteo explained, with attractor neural networks. In this case, you can associate the hidden patterns with attractor for the neural dynamics. And if the examples belong to the attraction basin of these features, the system is able, via neural dynamics, to reconstruct the patterns. So this is the set. Okay, as I said, the theoretical framework is the one given by Hopfield networks, And Hopfield networks are, of course, energy-based model in which you have the neurons, which are the sigma I variables, which can be plus 1 or minus 1, and they interact via a coupling matrix J. And this is a very simple statement of the model, but of course there is a lot of theoretical stuff in that. But what's interesting for our purposes is that the machine learning and true regularization scheme is associated with this choice of the coupling matrix. You can see that this coupling matrix is directly built from the training examples. And you have a parameter TD, which is strictly related to the regularization parameters in a machine learning approach. As you can see, that the training example are realized as random variables starting from the hidden features. This is contained in these two papers here. In another paper, which will be soon made publicly available, we proved also that in the Hopfield setting, we can implement the dropout technique via a Hebbian construction, in which the basic point is, you can see the pointer, yes, okay, in which dropout is realized as the dilution of the training examples from the outside. So this is an external technique to which is directly implemented in the construction of the coupling matrix. So in this case, the crucial hyperparameters is the dilution parameter, which is the probability to cut a bit of information in the training example. And these are the starting point for our theoretical investigation. The crucial point is that the training samples, as I said, are random variables, so themselves, the coupling matrix are random matrices. And so this is the point in which random matrix theory comes into play, because generally for a random matrix, the relevant information is encoded in a single function, which is the so-called spectral measure. And in particular, the crucial results in random matrix theory is that for larger matrices, the essential information is captured by a single function representing a given ensemble of random matrices. For example, Gaussian orthogonal ensembles are represented by the Wigner semicircle law, and the Wigner ensemble, the Wishart ensemble is represented by the Marchev-Pastor law. And this is accessible by random matrix theory tools. And in particular, in our papers, we derive the so-called asymptotic spectral distribution for both models I presented before. So what can we do with these results? We can, for example, inspect the dynamical properties of the Hopfield-like neural networks to investigate the generalization capabilities of these models. So, for example, the Hopfield network is a recurrent neural network, meaning that the evolution is a Markov chain, but you can unpack these dynamics, interpreting it as a infinitely deep neural network. So the input layer is a starting configuration, which in this case is a validation example. And then you propagate information across all the layers, and the output will be the response of the model. And of course, in the reconstruction task, we want to for the output of the model to be strongly correlated to the feature associated with the validation example. So it is important to ask this question here. So how close sigma infinity is to psi mu, which is the hidden pattern associated with the validation example. What can we do is compute the magnetization, as Matteo said. And if the magnetization of the last layer with respect to the feature we want to reconstruct is close to 1, the task is successfully completed. But in the theoretical case, this is a hard task because there is a full network of nonlinearity, so it is not so simple to compute this magnetization here. But we can get an idea of what's going on by simply computing the first step of dynamics. And in particular, we can compute the overlap of the first hidden layer with respect to the hidden feature. And of course, if this magnetization is close to 1, the task is completed even at the first layer. But in general, if this magnetization is higher than the starting overlap of the validation example with respect to the feature, of course, we are going towards the hidden feature. So in this case, we can expect that this situation can hold also to deeper layers. But the basic point is that this magnetization here for large networks can be exactly written in terms of integral of the asymptotic spectral measure for the matrices I presented before. And this, of course, allows to make theoretical prediction and then compare them to the numerics, so to the reality, and try to infer general properties of these models. So, for example, in the first row, we have a comparison between the theory on the left and the numerics on the right. And even though there is a quantitative gap between the two results, you can see that the qualitative picture of the theoretical prediction of the numerical simulation is actually captured by the theoretical predictions. And in particular, you can see that increasing TD, which is related to the regularization parameters, the generalization capabilities are downsized, and in particular, they are only ensured for high-quality dataset, meaning that the intrinsic noise in the training dataset is very low. Also, in the dropout model, we have a nice agreement between the numerics and the theoretical prediction. In particular, what we observed in our paper is that for high-quality dataset, for a very large number of examples stored in the networks, it is convenient to dilute the examples in order to have a gain in the generalization capabilities. And this is also observed from numerical simulations. So the basic point is that even though we are analyzing the problem at one step, we have a qualitative picture of the model. Also, I want to conclude with an interpretation of these results. First of all, from Hopfield-like theories, we know that if we store vectors with a Hebbian-like prescription for the coupling matrix, we are storing these vectors as attractors for the neural networks. So in the case of the training example, there are primary attractors, which are exactly the training examples. But from Hopfield theory, we know also that there is a class of secondary attractors, which are combination of the stored patterns, of stored vectors. And in this setting, these are responsible for the generalization capabilities, because when we store a lot of training examples, they have, of course, their attraction basin. And when the number of training examples is sufficiently high, these attraction basins merge in order to form a deep well, which is centered around the ground feature, centered in the hidden pattern. So this is the situation which enables generalization in Hopfield-like neural networks. But we also know from previous studies that this quantity TD here, which again is related to regularization parameters, controls the width of these attraction basins of the primary attractors. And so if we increase TD too much, we are perfectly disentangling the attraction basin of the primary attractors, so they can be still attractive. And this is an overfitting regime because it is possible to reconstruct training examples starting from a validation example rather than reconstructing the hidden ground features. So this is exactly an overfitting regime. This is a theoretical picture, but it is confirmed by numerical simulation, because if you start the Hopfield-like model with a validation example and make the system relax towards a fixed point, and then you computing the distance between the final configuration and the hidden pattern, you can see that for low TD, there is a generalization phase because this distance is exactly 0. But increasing too much TD, you can see that there is a continuous transition to an overfitting regime, which can be confirmed by explicitly computing the distance with respect to the nearest example. So this is exactly what I explained before with these cartoons in this slide here. So this is what I want to say today. So I thank you for your attention, and if there are any questions. Yep. Okay. I mean, okay. Matteo asked what diluting the training example means. So as you can see, the training example in the general setting is obtained by starting from the grand feature, adding a multiplicative noise. In the L2 regularization case, this is a multiplicative noise, which is controlled by this parameter here, which is the quality, which quantify the probability that in the example, that bit of information is equal to the ground feature. In the dropout model, these chi variables can be also 0 with probability D. So you are cutting information from the training dataset. But I say training dataset because the dilution is applied directly on the training example and not on the validation example. So this is in some sense mimics the dropout model in the Hebbian storing rule. So it's a kind of operation which push away the attractors of the training examples in this picture here. Yo.
Okay. So next speaker is Donatella Genovese.
Okay, good morning. Thank you for giving this opportunity to take this talk. Today, I will present you a work that we did to introduce new models for interpretable particle collision detection. It is a work that we done in collaboration with the University of Liverpool, and it is actually under review on scientific reports. So first of all, we have to take that machine learning and deep learning model as increasingly used in LHC data for different tasks like particle identification, error reconstruction, and background subtraction. And one promising direction is to use graph neural network to address this problem, since you can interpret nodes as particle and edges as connection in the graph. And this enables the model to capture a complex relationship. However, classical graph neural network, like graph convolutional neural network or graph attention networks, often lack of interpretability. And here we propose a solution that has some building block inside that can be analyzed to track if they are aligned with physical properties. What we propose is a graph transformer with a mixture of expert layer. So basically, it is a standard graph transformer adapted to graph. So the attention is computed only between nodes that are connected. And then instead of the standard feed-forward network, we add a mixture of expert layer. The mixture of expert basically has a router network, which is trained to the side where the input has been gone. And then we have some experts that are basically single neural network with a few layers. We use the feed-forward networks with 2 layers and real activations. And so basically the router is trained to decide which expert has been activated with respect to the input or with respect to a part of the input. In the case of graph, the part of the input are the nodes. And then we put a classification head at the end, because as we will see later, we use this model for event reconstruction. So we need a classification head to define what is the events that we want to reconstruct. Here there is the sketch of the full model. So how you can see, we have a graph. The graph is passed through a certain number of layers, and we can look at the attention maps to see which node pays attention to the others, and we can also see also the expert specialization. And okay, that's the point. And so as you can see, you can also look at which experts are activated with respect to the different nodes. So now we present the dataset that we use to test this model, and it is a dataset of Monte Carlo simulated collision events. And here we use as signal the model that came from SUSY theory, which is a new physics SUSY theory, where SUSY stands for supersymmetry, while the background are the other type of graph, and they came from the standard model theory. So basically, the SUSY theory is a new physics theory, while the standard model is what we actually know about the particle physics. We have two different types of background because they came from two different types of physical processing, but they came from standard model both, and so we treat them as background. And the task is to perform binary classification. So basically, it's very simple. We have to reconstruct the type of the initial events, and the two types of events that we take account are signal and background. We construct the graph with a very simple structure. So we have each node is the results of a collision. We have different types of particle, the jet that are the came from the hadronization of quark, the big jet that came from the hadronization of big quark, the lepton that could be both a muon or an electron, and the last node, which is energy, is not really a particle, but is a proxy node that is used to take account all things that are not detected, like, for example, neutrino or dark matter. And this particle has a certain type of features. The most important one are the features, the first three features that are the features that describe the dynamic after the collision of this particle. Here we have the hyperparameters that we set for the model, and we also test some different model like graph convolutional network, simple multi-layer perceptron, a graph transformer, and then at the end our mixture of expert graph transformers. That is the one that has the high accuracy and the highest area under the rock. I didn't put it here, but our model, through to the use of mixture of expert, enabled also to do less operations in terms of flops. So it is also speed ups the training and speed ups the inference process. Here we can see some explainability results. We can see the attention maps of the correctly classified signals and correctly classified background. As we can see, the first layer has a higher magnitude, while the second one shows a reduced magnitude. This is because the second layer probably do a refinement of the features. And in the first layer, the primary attention focuses on lepton and energy and on the widgets. And finally, here we can see also the expert specialization for both layer 1 and 2. And as we can see, we have, for example, in the first layer, expert 2 and 4 focus on lepton and energy nodes, which are crucial for distinguish signal and background, while expert 1 and 5 specialize on widgets, and expert 3 and 4 specialize on jets. And it is really cool because our mixture of experts is able to recognize some characteristics of the physics. For example, they specialize on the same type of the particle, like jet, widget, and then lepton and energy that are connected in a certain way. And so it gives some insight into the model, and it confirms that this model works well and is learning something that is physically meaningful. So as future improvements of this model, the first things that we are going to do is to test the model on different data sets to verify its applicability, because this supersymmetry data set is very simple. So we want to improve also the to test the model also on graphs that has more nodes, and also that has different types of connectivity. And also we want to evaluate the ability to generalize across different high energy physics tasks. In this case, we tried with the error reconstruction, but also, for example, generation is a task that this model can address, and that it is very important in high energy physics experiments. And finally, we want to try also to integrate large language model for automated accessible explanation of this model. So thank you for the attention. So yes, basically we have different types of data set. You can you reconstruct this data set from particle collision. So basically you can choose which node you want to use, and you can make the model greater than this one. So it is the data set that we have is processing that some physicists do, but so they can make the dataset also higher by adding some other types of jets or some other types of widgets and so on. Yeah. No, they were used also in other types of model, even in a vision transformer, etc. It is debatable on what they are meaningful or not. So, for example, in large language model has been demonstrated that sometimes they are not meaningful. So it's debatable, and the thing I feel is that that we don't have a metric for understanding if they are actually explainable or not. So that is the problem. Yeah. Yes. What we did in this work is to ask to expert evaluators if they were meaningful or not. But even to find a metric which understand if they are meaningful, I think it would be a good advantage. So.
Our next speaker is Silvia Marconi. Okay, to require access. Just a moment. I don't know why we already did this before, but now it's not working. Maybe because we saw it before. We checked all the links, so I don't know why, because it says something on the connection rather than on the. Proviamo con questo. So it's something for, with Roma 1. Next one is progetto Yara. So rete. No, è rete Uniroma forse. Ok, vediamo. Ok. Okay. So next speaker is Silvia Marconi. The stage is yours.
Thank you for the presentation. Okay, I'm from the Department of Methods and Models for Economics, Territory and Finance. The work is in collaboration with Vittoria Bruni, Giuseppina Monteverde, and Domenico Vitulano from the Department of Basic and Applied Science for Engineering. Let's skip that line and go directly to the topic, source camera identification, that consists in finding the source of an image, that is the device that took it. This topic is of interest in digital forensic and criminal investigation, as with availability of personal devices and the possibility to share images with the social network. Images have become part of everyday life, but sometimes are used in a malicious way, and so it can be useful to trace the origin of the images. Here we work in a closed set scenario in which we are supposing that we have a predefined set of cameras, and we have at our disposal a set of a sampling image for each camera. But how can we associate the image to the right camera? Well, this is typically done by considering the noise that is released on the image during all the acquisition process. This is a noise that is not visible to human eyes, but is a sort of fingerprint left on the image by the device. For example, the lens can cause aberrations, the color filter array, the mosaicing algorithm, the post-processing like gamma correction, white balance, and decompression in a usable format like JPEG, all leave traces on the image. But the most important component of the noise is given by the sensor, that is the core of the camera. It gives pixel effects, sensor dust, and dark currents but in particular the PRNU, that stands for photo response non-uniformity, that causes the non-uniform response to light by the pixel that compose the sensor, caused by the imperfection occurred during the manufacturing process. So being a characteristic of the single sensor, the PRNU potentially allows to classify the images not only by brand and model, but even by the single device. Mathematically, a natural image can be modeled as a function I, and then a multiplicative term k that stays for the PRNU, and an additive term n that accounts for a random noise. In case of a flat field, that is an image acquired in a uniform condition of light, the image is a constant. To extract the PRNU, we apply a denoising filter. Now, typically one applies a denoising filter to remove the noise. Here we want the noise, and so we subtract from the image the noise of the image, and we get the residual that contains the noise. But while for flat field images, the residual is representative of the PRNU, this is not the case for natural images, where, as we can see from these three residual obtained with the three different filters, there are some artifacts above all in the points where there is high gradient variations. And so this procedure tends to destroy the PRNU that for this reason could not be the feasible tool for image classification. We address the problem with a convolutional neural network in a supervised learning approach. We give as input to the network the images or patches, so with or without preprocessing. And during the training phase, the CNN learns this association between the images and the labels. And then during the test phase, the network will make some prediction on the unseen data. In our framework, we are considering a possible realistic scenario in which we have a small number of cameras, and we want to use a publicly available network, the GoogleNet, that has been pre-trained on the ImageNet database, and it is able to classify over 1,000 different objects and environments. But here we don't want to test this ability of this network, but we want to test its ability to see the underlying pattern in the images. The key aspect of this method is that we don't classify the PRNU for the reason that we have already said, but we classify directly the original image. To reduce the complexity and save memory space, we consider only the green channel where the PRNU most concentrates, and we will apply some techniques like the image partition and image enhancement. The final goal is to find a trade-off between the computational time and accuracy. So we don't claim to reach the best accuracy, but we want to fix a computational time, here for example 20 epochs, where an epoch is the number of iterations that the network needs to process all the training images, and try to find strategies to improve the accuracy. If we use the patches of the image, we apply the majority voting technique that consists in associating to the image the most recurrent label that has been associated to the patches that compose the image. The same thing we will do if we consider, instead of the patches, different versions of the same image. For example, the image treated with different enhancement procedures. The enhancement that we use are the image adjuster that saturates the top and bottom 1% of the pixel intensity, the histack that performs the histogram equalization so that the output image has a uniform distribution, the adaptive stack that makes the same things but on a small region of the image, And the fading, that is a homemade procedure that is based on the Lipschitz regularity of the luminous channel. And now we are ready to see the experimental results. We consider 4 devices, smartphone from the Vision database, and consider 200 images for each camera, considering 80% for training and 10% for validation and test. If we classify the PRNU, we obtain 76.5% of accuracy, and if we classify natural images, we obtain 74.25. This is a surprising result because we expected the contrary. But we have already seen that in the case of natural images, the PRNU is not a so effective tool. Also, the result on the natural images is not a good result, clearly, and so we apply strategies to improve this accuracy. We observe that if we apply the enhancement, the accuracy increases. In particular, we reach more than 80% if consider the 4 enhancements together, or the 4 enhancement and the natural image. But if we see on the right panel, we see that all these experiments suffer from overfitting, clearly. Overfitting that occurs when the network learns, performs well on training data, the blue line, but fails with the validation data, the black line. And so to avoid overfitting, one of the strategies is to increase the number of training images. To this purpose, we partition the image in 2x2, 4x4, and 8x8 parts, and consider the enhancement of the patches and apply the majority voting technique. In this way, as we can see from the right panel, the accuracy increases with the increasing of the partition, and is higher if we apply one of the enhancement. Here, for example, the image adjust, but the same happens if we apply the other enhancements or the 4 enhancements together. So we can do even better. For example, partitioning the image in 108 square blocks of size 256, reaching more than 69,000 training elements. With majority voting, we reach very high performances, 98.75 with the image adjust, for example. And now, as we can see from the right panel, there is no overfitting anymore. This is another experiment with 8 smartphone, but is very similar to the previous case. From the confusion matrix, we can see that in case we have 8x8 partition and we apply image adjust, only 4 images are misclassified. So I can conclude, here we are working in a noisy framework, and the fact that the PRNU is affected by the denoising procedure introduces uncertainty and partial knowledge. That is the topic of our task within the work package 5.7. But if we classify the images, the original images instead of the PRNU, we mitigate this uncertainty, improving the reliability of the model's decision. Moreover, with the majority voting, we extract more knowledge from the raw data. The contrast enhancement increases the accuracy, making the model's decision more interpretable. The dataset segmentation with partitioning reduces the overfitting, improving the generalizability of the model. And so I can say that this method, in some sense, helps to improve the solution quality, even if we are working under uncertainty and partial knowledge. And that's all. Thank you for your attention. we thought this tool for the forensic field, the criminal investigation. I met a policeman that told me that they have a lot of data, but they don't have the tool to find the source of the image. That is a very important topic for them. I didn't know. And so they have not the issue of privacy. The police. Yes, but when one works with images, there is yeah. See, yeah, this is. Yeah, I think that's a problem. That's a problem. Thank you.
So last speaker, it's from Leonardo Espia, and it's Ramul Nadarpur. I don't know if I pronounced it well. I'm sorry. Welcome.
Hello, everybody. Thanks for being here. Today, I'm presenting you the project Yara, which is in collaboration with Sapienza University. And the focus of the project is working on trustable AI models for radar applications. And by trustable, we can point out to 4 different pillars of transporting AI, for example. And we could have an explainable model, or we can focus on the generalization power or uncertainty quantifications. But in our case, we decided to put a bit of effort behind the robustness aspect of the models. And by robustness, we meant that we want to make sure that the model's performance is somehow guaranteed when it faces an unseen data set that is pulled out from a different distribution. So we have a different distribution of the test data set with regards to the training data set, and we want to make sure or also move towards designing a robust model, which is the case in real world application that we launched the model in real world, and probably the data that it sees has a different distribution that with regards to the data that it was trained on. So this is the case in particular for radar applications that many of them are safety critical, like autonomous navigations and in particular air traffic control, and also search and rescue scenarios. Also, we have less safety critical applications for environmental monitorings, like detecting the edge of the glaciers, for example. And we decided to move around on what is available online in the open source data sets for each use cases, and we try to get the best we can in terms of which data can be more useful for us to analyze the robustness that we are working on. And you can see many of the examples here, and by far we could see that many of the well annotated, well tailored, and well documented data sets were for autonomous navigation use case. So we decided to move towards that direction. And in particular, we decided to go for new scenes data set, which is quite famous in this field. And it has a really unique feature that it was recorded in Boston and Singapore, which I will point out later in the presentation why that part is really important. And it has around 1,000 scenes that was sampled at 2 hertz frequency. And between each sample, also you have the sweeps that can be useful for interpolation as well. And we had 3 types of sensors, the LiDAR on the top, 6 different cameras on different angles, and 5 radar sensors covering 360 degrees. And the data set is presented with bounding box ground truth, which is not useful in our case because what we decided to do was moving towards a more novel, let's say, approach in the autonomous navigation world, which is occupancy prediction. So you could have many classification heads for an autonomous agent, like object classification, object detection, curve detection. And one of the newest ones are occupancy predictions, which basically divides the surrounded world of the agent into small cubes or voxels. And then your model can predict if each voxel is occupied or not occupied. So it's a binary classification more or less. But on top of that, you could have a semantic segmentation head, let's say, to classify the cube as well. And another good feature of the new scenes was that we have another data set that was tailored to new scenes, which is called OCC3D. And it can be used as a ground truth for occupancy prediction. So you have all the tools to work on this data set. Another issue, another point that I want to make was that many of these occupancy prediction architectures in the literature either focus on purely vision approach or a mix of vision and LiDAR. And you could see few of them that they take radar measurements as well. And we can say radar adds another benefit to LiDAR and camera, for example, in harsh light situations or like in foggy weathers, or the ability to see way more distance with respect to camera and LiDAR. So you could get benefit from radar as well. And another issue was that many of these architectures are super complex and they're working on big data sets. So it's really difficult to maintain and retrain them again and again. So we decided to also investigate to see if we can change anything and make it more efficient, at least. So as an example, we have many different approaches in occupancy prediction. One of the most famous ones is the BEV fusion that you can see on the top right, that was used in many other papers that were derived from BEV fusion. And it uses a mid-fusion's approach that basically fuses the feature map of the image and LiDAR, or you can also radar as well. For example, on the bottom right, you can see again a mid-fusion approach that was derived from BEV fusion as well, another paper. And on the left, you can see another paper called Hydra, another approach that uses a hybrid approach. So you would have a cross attention at the first step between the radar and the camera. And in the end, again, we have the radar pillar points and the fused camera radar points, again, fused together. So it's a hybrid approach. So there are many things that we can do here. And we got an idea that maybe we can analyze the effect of these fusion approaches on the robustness of the model. So we are moving towards that direction to test which fusion step, either early fusion or mid fusion or a hybrid one, delivers you a more robust network. And by more robust, as I said earlier, we need to have a measure to we need to have a mean to measure the distance between the test data set and the trained data set, and we see how the model performs with our desired, let's say, metrics. And to do that, we can to create that distance between the training and test data set. We have two approaches. The first one is to go out and record new data set, which is different from the training. And most of the times that costs a lot of money and time. But I pointed out that the new scenes data set is recorded in Boston and Singapore. So inherently, it gives you the ability to do the training on one city and do the inference based on another one. So you do the training on Boston, for example, and you do the inference based on on Singapore. But that's not always the case. So in the next step, we are aiming for generative AI to create that synthesized shift, let's say, in the data. So these two approaches are, let's say, the main pathways that we are moving towards by now. So at the moment, we are training the model. I mean, the results are not out yet, but the challenge that we're facing now is the sheer size of the data. It's around 600 gigabytes, more or less. So with 4 GPUs, still it struggles to be trained. So we are working on making it more efficient, either by skipping some steps or reducing the size and the resolution of the voxels. So that's the current state of the project, and it's being trained on the DaVinci HPC of Leonardo. And in the parallel way, also we're investigating the generative AI approaches to either by, for example, using diffusion models to create that synthesized data set that can be used for testing the robustness of the model with synthesized data that has a different distribution. And thank you. I mean, sure. Yeah. Yeah, the problem was the availability of the open source data set, that most of them lacked the radar measurements. So in also other use cases, for example, like in search and rescue that I didn't show here, but you had basically the radar measurements that you could see behind the walls, any activities that are used for like rescuing people in earthquake, for example. But the data itself was just an image of the, for example, the range. It wasn't the pure radar data. So we're kind of forced to move towards this data set. But there is another challenge of we can basically eliminate also the LiDAR and images as well, but there isn't so much semantic information in the radar, which is so sparse. So we're kind of in an odd space that the radar data, the open source radar data set is not that available to do that performance. And also, if we are going towards this autonomous navigation, we are forced to use those images and LiDAR. So, I mean, we have a HPC to use, but yeah, that was the main motivation that we did this. Yeah, actually, we're at the moment, yeah, we're doing this game. Okay.
Se è stato un problema generale di connessione. Abbiamo Angelo, mi sa che viene adesso, se no lo faccio io e Michele.
Okay, so we continue with our session, and the next speaker is Angelo Oddi with an empirical study of grounding PPP DDL plans for AI-driven robots in social environments. Thank you.
Thank you for the presentation. So thanks for the invitation. This is in joint work with the work package 5.3 and the transversal project 4. So it's a collaboration between CNR, our institute, the Institute of Science and Technology of Recognition, and Sapienza. And also, this is one of the collaboration with our institute. We have several projects in PNRR, and other collaboration are about social robotic and assistive robotics. So this is an example of collaboration. Okay. In this, sorry. Oh, okay. 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 So in this talk, we have this general question: how an autonomous robot acquires knowledge and skills to solve problems that are not predictable at the same time. So in one word, how we can improve the autonomy of a robot. So humans are able to, are autonomous for sure. So are able to extract information from the context, to abstract the reality into symbols, and can learn continuously from the environment and adapt themselves. So in some way, we can try to do the same with the robots. So to emulate these human capabilities, this is our general framework. So in robotics, generally, you think about a robotic agent interact. There is a paradigm, is the so-called sense and act paradigm, where we can try to do research about how a robotic agent can interact with the world and solve problems. We have extended, so we do research in extending this paradigm. So we call this from the sense and act paradigm to the discover and act paradigm. So the robot, during the interaction with the world, try to learn new skills, and so it can try to use these skills in solving new problems. So our idea is to integrate learning and symbolic reasoning, that is planning. And what we do is to learn new skills and abstract this new skill into a symbolic format. Okay, so our basically we do a simulation. So our framework, we do research for now with a Tiago robot and into a simulation environment where our Tiago, first of all, have to learn some basic skills. And these basic skills are about object manipulation, navigation, and also interact with humans. So, and this is why this session, we call it maybe, it's also about social robotics. So we try to simulate how a robot can interact with a human and also learn new skills. So this basically our contribution. First of all, we have defined a control architecture, which is an extension of the three-tier architecture, which is a classical way to construct a controller for a robot. The three-layer architecture has three different layers: the decision layer, the executive, and the functional layer. At decision level, it's possible to define a high level, to use symbolic knowledge and define goals and generate plan to achieve this goal. The goal and the plan can be executed or in a simulation environment or in a real environment. We add, so in our system, the idea is to also the robot can interact with the environment, collect new data, and learn new skills, and convert these new skills into a symbolic p.2. So the idea, our empirical, what we are proposing in this talk, is the idea to use in our architecture. We can generate a set of training plans with the ROS plan, and these training plans can drive the robot in doing some experience. But what about the difference? Because the plans are ideal instead of the environment. In the environment, we can simulate uncertainty, and also the robot can sense the environment with noise. So we train the robot with a set of plans, but during the execution, some uncertainty change the behavior, the ideal behavior. And so what we can generate is an output, so a new knowledge which takes into consideration the real behavior of the robot. So we can represent, for example, new symbols, and the fact that one action can have different outcomes. So the input is an ideal planning domain description language, and the output is a probabilistic planning description language. So we are able to capture the uncertainty of the environment. So the first contribution was the ROS architecture. The second contribution is a dynamic, realistic simulation of an environment where the Tiago robot can, the behavior is affected by uncertainty and noisy perception. And so, in this study, this was presented at the last ECAI conference, we investigate how the training behavior of the Tiago, so by following different plans, so by executing a set of different plans, so a sequence of action, these actions are represented in extended way, where the ideal action is also represented in p.2. So one action can have different outcomes instead of only one. And so the method is applied, is to collect, so put in execution several plans, and we train. So this is the training phase of the robot, and the outcome is collected in a set of we collect the data, and the collection is at a level, at some symbolic level. So we have each when we execute an action, we collect the initial state and the effects. And the state is a list of variables. One are continuous, other are discrete. For example, robot position, the gripper position, and so on. And we run several experiments. So the robot moves, for example, from one table to the door 1, or move to the door 2, and collect the state and the effects of the action. Or the robot interacts with obstacles or with person. And so during this training phases, there is uncertainty and there is noisy perception. For example, in this case, grasping a person is failed, or the object is fallen during the motion of the robot. All these events are captured during the training phase. So a training plan is a set of action. Each action, we store the initial information and the effective information. Yes, information means the state. And so we can generate at the end new operators. New operators, for example, there is this is a p.2 representation of the operator to move from the door, to move the robot from a table to the door. And there are two different situations. One situation is where the door is free, and the other one when there is a person close to the door, near to the door. And these are the representation of the symbols. Okay, so in conclusion, we have presented how to we have presented a system and a control architecture which is able to learn new knowledge in symbolic form. And the idea is to use these capabilities of generating new knowledge in a social environment. So it's possible to think to do some training where the robot interacts with people. And in this case, we can think this as a catalyst for long-term autonomous capabilities of the robot, to improve the long-term autonomous capabilities of the robot. And also, the idea is to study how to improve also communication skills of the robot with humans. Okay, thank you. Yes. Okay. 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 See, in this case, we have a set of operators, of skills. During the training, the robot put these operators in execution. So, and each time, for example, when they place an object, store the initial state and the final state. We collect this, and the representation of the symbols is we use a different representation, but the effects is each symbol is represented like a kernel density estimator. So we collected the set of possible value, output value, and generate a kernel density. Okay, but yeah, this is a problem. But because now in the current version of the architecture, when we execute one option, one operator, we store at the start and the end. What happens during? This is a problem to solve. In addition, we for each options we know which which part of the state is changed. So what we represent is only a kernel density estimator of the changed variable. This is the idea. And also there is an important feature in the point of view of the robot. So we represent the symbol is from the point of view of the robot. The symbols are only the effects of the options, are not defined. So it is a robot-centric perspective. And so the important achievement, we use the abstraction procedure. We basically execute the set of options and we classify the effects as a symbol, but also we match the effect symbol on one option. For example, we are able to use a common vocabulary to represent the effects and the precondition of all the options. In this way, we are able to link the effect of one option to the precondition of another one. So after this training, and this is, of course, after this operation, we are able to do planning. Otherwise, you have different names for the effects of one option and the precondition of the other one. So the abstraction has this property, so are able to generate a common vocabulary for all the options introduced in the domain. Okay, only if you are able to train it. So suppose you in this case we have the set of options is predefined, and we generate new symbols which takes into account the uncertainty of the value. But if you want to add a new operator, you of course have to train. For example, you want to grasp an object in different way. You have to do this training and add it in the set of options and so on. Okay, thank you.
Okay, we can move to next talk that is generative AI-driven social robots from Alessio Saladino. Okay, so it's yours.
Thank you for your introduction. This talk is related to generative AI applied on social robots, and more specifically, a large language model applied to social robots, because it can be a very fruitful integration, since it could allow to adapt the robot behavior to act in a human-like way without the need of classical programming. So the large language model is the one that will decide what the robot will say and do. But of course, these do not come without problems. In literature, we already have studies that tried this kind of integration. But what I've noticed is some lack of attention towards the safety aspect of this integration. In fact, the large language model suffers from a wide variety of problems, such as biases and hallucination, that can be also amplified during the integration with a physical embodiment, which can also potentially physically hurt a human being. So it is really important to try to find ways to mitigate this kind of dangers. So during my master thesis, I developed this architecture that aims to orchestrate the robot behavior in such a way
to make it act more safely when mounting a large language model. And so in the top right corner, we just have the input-output part of this architecture in which the robot communicates with the user vocally and by performing some simple actions and showing some simple emotions. Then we have the four main components of this architecture. The first one is called the social supervisors that ensures that what the user is saying to the robot do not contain any socially unacceptable concepts such as, for example, discriminative words or bad words. Then we have the database module, which works as a long-term memory for the robot, in which we store all the information that we want the robot to know related to a specific domain. Then we have the functional supervisor, which is the module that uses the knowledge stored in the database to reason about this potentially the safety of the interaction. And finally, we have the conversational module. That is the module that builds the final answer in terms of what the robot will actually say and do. So by starting from the first one, is the social supervisor that just analyzes the input sentence to determine the harm level from a social point of view. So depending on the danger of the input sentence, it may handle this sentence differently. For example, it can fully reject the sentence if it is very, very biased. It can slightly modify the sentence if it contains some terms that may be dangerous, but maybe the sentence itself is not so dangerous. And finally, it can accept the sentence as is if it is completely safe. The final output of this module, in any case, will be a sentence that do not contain any harmful content, in such a way that the other components may use it to perform the reasoning without any biased content. Then we have the knowledge-based module, which is the long-term memory of the robot. And we use this to store into a vector database the information related to the domain in which the robot performs. For example, the files related to a university domain. But also we can store in this database information related to the users that interact with the robot and also the history of past conversations. So this allows the robot to remember what was told in previous conversations. And during the runtime, by using retrieval augmented generation, we can vectorize also the input sentence to the user to extract the most relevant documents, and then another large language model here called the question answering module will summarize this document by extracting the most relevant information. And this information will be used by the functional supervisor that will reason about the safety of the request in terms of, let's say, in terms, depending on the context. So, for example, some requests may be apparently safe, but in certain contexts, they may be dangerous. For example, if a user asks to the robot to provide some food, this is basically a safe request. But if that user suffers from food allergies and the robot doesn't know this, following that request may result in a dangerous outcome. Thanks to the database and the functional supervisor, the robot may use the relevant information to reason about a potential danger. Finally, the conversational module uses all the outputs coming from the other modules to determine the robot output, which is expressed as the final answer, so what the robot will actually say, the action that it will perform, and the emotion that the robot will show. This framework was tested on the Martina social robot that we have here in Diag, and we tried to run different experiments. The one I want to focus on is asking the robot to move both the arms while one of the two arms, the right one, is holding a dangerous object. So the flow of this framework is the following. We start with the user that asks the robot to move both the arms. This input is analyzed by the social supervisor. In this case, it's assessed to be safe because it do not contain any dangerous word. Then the long-term memory of the robots extracts the information from the memory to determine the fact that the robot is holding a dangerous object, which is a screwdriver in this case. And this information is used by the functional supervisor, to which we ask to perform a chain of thought reasoning to determine if the request is safe or not, depending on the context that is provided by the database. And in this case, it wasn't safe, of course. Finally, the conversational module is the one that builds the final answer. In this case, we have the robot saying that it cannot move both the arms, but it will move only the left one, because the right one is determined as unsafe in this case. So, of course, this architecture is some sort of starting point. It can be further expanded, for example, by adding vision supervisors that could allow the robot also to visually analyze the surrounding environment. And this will be done by a master thesis student, or we can expand it by allowing the robot to perform more complex movements. But what it is important is that just mounting an LLM on a robot is not sufficient, because the robot, the LLM will probably not understand the fact that it's mounted on a physical embodiment. So it can hallucinate much more. So having a surrounding architecture that drives the behavior of the LLM, it can be helpful from a safety point of view. So to conclude, I say that I think this kind of research field will be further explored in the next few years. We will see many large language models mounted on robots, but what it is important is that we do this in a safe way. Also, ideally, we want, and it's what we are trying to achieve also with this architecture, something which is more generalizable. So the robot is not programmed to work in a specific environment, but depending on the information that it has in memory, and along with common sense given by the LLM, the robot can be used and deployed in multiple domains. So thank you for your attention.
Last but not least is Michele Brienza. They will talk about planning with the LLM.
Thank you. Hello, everyone. And in this talk, I'm talking about planning with large language model, and in particular, the work that we've done last year with our research group. It has been demonstrated that if LLMs are large enough, they can be used to decompose an high-level task to a sequence of steps that represent sequence to solve a task. And they do that thanks to common sense knowledge that acquired during the training, thanks to the large amount of data that they used. The problem in this case is the fact that the action are hardly deployable in a real scenarios, because the words contains nuance of the word, because I can say go to a position with a a large number of words, for example, walk, navigate, go, and so on and so forth. And the problems, other problems are the limited context window that I have to input the scene to the LLM. In fact, I have to describe the scene to the robot or the agent to describe the situation in which the agent is. And the problem that visual language models suffered the bag of words. They answer with the objects in the scene, but often we lose the spatial relation between the objects in the scene. And autonomously and evaluate the plan autonomously is extremely difficult. In this work that we presented last year, we developed an architecture to generate a plan with a multi-agent architecture. The basic scenarios consist of an agent that take in input an image and a task, and as output provides a plan. But in this case, if we use an LLM, we can obtain hallucination because the LLM can generate in the plan objects that are in the scene, because the LLM try to generate a plan also if the objects are not in the scene, and we want to avoid this situation. To do this, we developed an architecture with three agents with three different roles. The first one is the semantic knowledge miner agent that takes in input the image and the task to solve and generate in a knowledge graph as answer that contains in the nodes the objects in the scene and in the age the spatial relation between them. The grounded knowledge miner agent map this description in a textual manner in which we describe the objects to use in the scene to solve the task. For example, in this case, we will have the bread to put in the fridge is on the countertop, and so on and so forth. These two outputs, the graph and the description, are given in inputs to the planner agent that provide us the sequence of extraction to follow to reach the goal. In this case, in a list of steps, we have pick the bread, put it in the fridge, grab the knife, rinse the knife. But when we have obtained this plan, how can we automatically evaluate this plan? In literature, a metric is published, and this metric takes the ground truth plan, the predicted plan, and compute a set of action phrases and check how many action phrases in the ground truth plan appears in the predicted plan. But this metric doesn't evaluate the semantic similarity between the words and the action. And in fact, in this case, we see a ground truth plan in which the socks are before verb, and then the left show and right show. In the predicted plan, the sequence are shuffled, and so doesn't respect the same order. And in fact, in the predicted plan, we before were the right sock and shows, and then the left sock and left shoe. In this case, CAS give us a metric as a similarity score of 0.33. So we developed a new metric to evaluate the plan generated by LLM that leveraged the natural language structure, and we developed two components: the sentence-wise similarity and the goal-wise similarity. The sentence-wise similarities find the most similar sentences in the predicted plan in the ground truth plan and compute the similarity score of all the sentence, while the goal-wise sentences, before to evaluate and compare the action and the objects, we compute with spaCy a post-taggings extracting the verbs and the nouns. In this case, the verbs represent the action in the sentence that represent the action that we do in the scene, and the objects involved in that action. In this case, we compute with the word embedding the similarity between only the action and the noun involved in the action. And then we compute the the final score using alpha parameters that allow to evaluate with average the goal-wise similarity and sentence-wise similarity. And in fact, in this case, we obtain a value of 0.83. This architecture we run different tasks, and we demonstrated that multi-agent architecture with our metric and other metric allow to obtain better results in comparison of a single agent architecture. This architecture is we put this architecture on an embodied agent. In particular, if we want to use LLM in a real scenarios, how we can do that? And we developed this architecture on a Tiago robot. And in this case, for example, we asked the robot order the shelf to have 2 objects for level. The visual language model has to understand that we have 3 levels and the number of the objects for level. And in this case, we have to put the trophy cup in the middle shelf, for example, and the ball on the bottom shelf. To do this, we use the architecture that we see before, but in this case, for the planner agent, we put in a set of action that allow to map the action of LLM to be executed on a Tiago robot. In fact, we map the action grab in order to move the arm of the robots near the objects and close the gripper in order to pick up the object. And so in this way, we done for the other actions. After this, the objects that we have in the scene graph are extracted to pass them in a Hello World architecture using natural language processing techniques. And with Hello World, we detected the objects in the scene, and we obtained the mask with segment anything model. After this, we use the relation namely the spatial relation in the edges of the graph to identify which specific objects is in the scene. In fact, the classes of Hello World is shelf, but we have to demystify which shelf is bottom shelf, top shelf, and middle shelf. And in this case, we use the spatial relation in the edge to label the specified object in the scene and retag so the real environment perceived from the robot. When we have this, we put the plan generated by LLM and executed with the low-level mapping of the action that I've described before to execute the task. We demonstrated this on different experiments in our laboratory, and you can see the results on the website. Thank you for attention. Okay. In this case, the goal is generated by LLM, so it's not replicable. So in the first try, we can put the trophy in the middle cup and the ball on the bottom shelf. So we don't put it a constraint in the LLM, but if in the description we describe the order the shelf to have 2 objects per level, moving the trophy in the bottom shelf and the cup in the middle shelf, the LLM execute the plan in this way. Yeah, every possible is good. Okay. Yeah. Maybe maybe the LLM try to pick also the object that cannot be manipulated, and we are working to avoid this. No, we are not. Yes. We are working on this to avoid the situation, adding constraints to plan, integrating the self-awareness of the robot, because we want. Yeah. Yes, because in the literature, this kind of architecture are described as just on each prompt, each module that uses a prompt is called an agent in the literature review. But yes, yeah, but in this case, the semantic knowledge miner agent, yeah. We call it agent because use a prompt is a module, and so it can operate on the scene to obtain an answer that represent our desired answer.
So this was the last talk of session 4. I leave the stage to Luca.
Yes, I have very close concluding slides. Before lunch. So first, thanks again, everybody, yesterday and today, to attend this workshop. It's been very nice. We started yesterday with a very broad overview of what have been the main research results in all the work packages, and then during the sessions we have seen very nice talks that clearly demonstrate the high quality research that we are doing in this book. I also mentioned that for most of the KPIs, we are largely above thresholds. And again, thank all the researchers in this book to achieve this goal. Now I want to just make a conclusion to illustrate what will be our next steps. In particular, about a little bit focus on KPIs that were planned for the third year of the project. So now it's time to consider all of them. And also I want to give you an overview of next scientific and dissemination events very quickly. So about KPI focus, I would like all researchers in this book to think that in the third year we'll have to focus on this, in addition, of course, to all the others. So you will all continue to do your wonderful research and publishing your papers, but we have also to consider in particular these KPIs for which we need a little bit of more effort in the third year. One is benchmarking and data sets. So we have seen also in the presentations today that especially the session was about machine learning, that of course is using data set. So please let me know or plan if you are building a data set or a benchmarking tool or benchmarking activity that is part, of course, of the FAIR project. We will be very happy to include this as an outcome of this project. So this is something that I invite all the researchers to think and contribute to this set of KPIs. Another aspect that it's very important for the project, of course, is dissemination. We are doing very, very well in dissemination in scientific venues. We can do a little bit more when we want to disseminate our research in, for example, in magazine for general public or industrial magazines. So I would like to invite again all to think about having, for example, some papers in specific magazines, industrial magazines or general public magazines, to show our research results also to a general public and not only in the scientific communities. Another very important topic is to balance gender. Unfortunately, it's very, very difficult. Again, in this room, the gender balance is not good. And that's something that we have a very ambitious target in FAIR to involve female scientists at every level, of course, in the scientific activities, but also in the simulation events. So this is something that we also consider. We know that all the world is facing this problem, that this kind of research is mostly, I don't know why, but it's more focused on increasing this kind of gender. So we will really need to balance this, and we'll do our best to reduce the gap and make sure that female scientists can be involved in these activities. If you have an idea of any way of putting this more in practice, this will be very, very welcome. Another thing is that we need to involve more researchers, in particular young researchers, in industrial activities. This is something that, as mentioned yesterday, we will cover when the industrial projects that are funded with the second cascade call will start. This will happen very, very soon. And as soon as the winners of this call will be publicly known, I will invite all the young students, in particular the researchers, to see if there is any opportunity for them to collaborate with the companies. And also for PhD thesis, it's very important to consider multidisciplinary and industrial involvement. And so we will involve more and more researchers from other disciplines with respect to AI, but also with industrial background as part of the thesis committee of PhD students, because this is also important to have some feedback from outside the standard AI research field. And more in general, we have to enlarge in this third year the community of stakeholders of FAIR. So any initiative to involve more and more entities, companies, or people, researchers in the family, in FAIR family, is very, very welcome. So this will be some sorry, the focus that we will have in the third year with respect to the KPIs. Again, in addition to continuing to do the wonderful research that we are doing. So just to announce a few next scientific meetings, we will have very, very soon a kickoff meeting to introduce the industrial projects that will start, that are funded through the cascade calls. And as mentioned before, this will be announced to everyone to start collaborations also with these companies. There will be 5 projects in total that will start soon. We will have very soon a review meeting with the external experts. And for this, we have to be very well prepared again to show how well we are doing, and no doubt about it. Also, I will ask for contributions to all the work packages, and also at this point, all the projects and also the affiliated partners to contribute to the success of this review meeting that will happen in a few months. We are planning for a PhD school or a PhD course on adjustable autonomy and physical embodiment that will be part of Transversal Project 4. We are also waiting for initiatives like this from other transversal projects. We will definitely organize more specific workshops. So this one has been a general workshop in which we have seen all the topics that have been addressed during the research in this book, but we are also targeting more specific workshops, usually organized by the transversal projects, but also this can be organized by a subset of researchers who are interested in a particular topic. For example, we are discussing about organizing a workshop with the CNRRs exactly on the topics of social robotics and generative AI. And so invite all of you that you can organize a nice workshop on physics-informed machine learning. So I invite all of you, if you have idea of organizing topic-specific workshops on subtopics of FAIR, to let us know and to advertise this. And then we will have workshops with the winners of the Cascade calls to, again, collaborate with them. I also want to announce that we have done the workshop of Spoke 5, but all the spokes in FAIR are organizing workshops like this. Everything is available on the FAIR website. So two of them, as you can see in the slides, have been already run. The others will follow in the next weeks. And all of them are also online. So I invite all of you at least to give a look at the program that is usually published maybe 1 or 2 weeks before, and attend them, because all the other spokes in FAIR are doing also very good and nice research, and you can find opportunities to collaborate also with other spokes. That is also very important for us. So you can find all the information on the FAIR website as well. Okay, just about dissemination events. We will target industrial meetings. Last year, I forgot to mention, last year I was attending, for example, the Industrial Robotics Fair, BIMO is called, in Milan. And industrial robotics people are very, very interested in AI and generative AI to understand how to use AI to improve the quality and, of course, productivity and efficiency of industrial robots. And I think it's a very hot topic at this moment. It's very good that we attend this kind of meetings to show that we can actually contribute to improve performance in industrial settings. And also very important to have events for general public, distribution of general public. I just mentioned the very first one that will happen next week, that will be here, in which we invite many, many schools as orientation activity for high schools to orient them towards a university. And we will feature a demonstration that is mostly what Alessio was presenting in the previous talk, of a social robot that is driven by Minerva LLM, that's been also developed within the FAIR project, to demonstrate the ability of the robot to talk with students about university and department matters, hopefully without hallucinating and without saying wrong things. This will be for us also an experiment to put our technology on the wild and see what happens. And of course, there are more activities for outreach of general public. And again, if you have any idea about organizing such things, just let us know, because they are also important to reach our goals. I want also to mention that in March, there will be this very nice opportunity. This is reserved only to FAIR researchers, PhD, and research assistants. It's a placement program, which will be sessions on coaching, assessment, and virtual desk. And that also a very important activity in order to give opportunities to young researchers to have more space ahead in continuing their career, hopefully in doing research on AI. And so this is something that will happen here and in a few weeks in this department. But also in this case, this is a program organized by FAIR. If you go to the website, you can find also other programs. And finally, again, in terms of dissemination for general public, FAIR has collaborated with Il Post to produce a set of podcasts, dissemination podcasts on AI. And I think they are very interesting, and I invite all of you to spend some time, because they are not short, but maybe good while you travel, to listen about AI from, of course, researchers from FAIR, but of course with a goal of informing general public. Okay, so that's it from my side, and I don't know if you have any other final question or comment. Otherwise, again, thanks for coming, especially for contributing to the success of the results of Spoke 5 and in general FAIR. And I'm sure we'll meet in some of the other events that I just mentioned. Thank you very much. Okay, and so we close this